Yesterday we discussed the difference between how a parallel circuit and a series circuit are wired, and then we looked very in depth at the equations we use for a series circuit. Today we're going to focus on the equations for a parallel circuit. So, in a parallel circuit we have multiple loops. The current can go through just one path or any of the other paths. So the current is split up among the loops with the individual loop currents adding to the total current. It is important to understand that parallel circuits will all have some position where the current splits and comes back together. We call these junctions. You can think of these like junctions on the road. That's a spot where you can choose to go in one direction or another. The amount of current that goes into a junction must equal the amount of current that comes out of the junction on the other side. So if we take all of those sentences and turn them into equations, we get that I total equals I1 plus I2 plus I3 plus I4 and so on, according to how many resistors or loops we have in our circuit. And then we get I in equals I out. As for the voltage of a parallel circuit, the voltage will be the same throughout the whole circuit. If we go back to the obstacle course analogy we discussed yesterday, it's like you're competing in the obstacle course, but you can take all of your energy, go through the circuit, complete one obstacle, go back, pick up a little more energy, and go back and complete the second obstacle. Okay. If we combine the idea that the voltage is equal with the total for the currents using Ohm's law, which says voltage equals current times resistance, and then solve for current, we get 1 over the total resistance is equal to 1 over the resistance of light bulb 1 plus 1 over the resistance of light bulb 2 plus 1 over the resistance of light bulb 3. We say that this is the reciprocal sum of the resistors. If you don't remember this symbol is sigma, which is a Greek letter that means add. Let's try a sample problem. The first thing we're going to do is label resistor 1, resistor 2, and resistor 3. We know we're going to work with a parallel circuit. So, the first part of our question asks us, what is the total resistance? We know our equation for total resistance of a parallel circuit is 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Using the numbers that we labeled in the diagram to the left, we get that 1 over the equivalent resistance equals 1 over 5 plus 1 over 7 plus 1 over 9. With this many fractions, the simplest way to add them together is to convert them to decimals and then add the decimals. We could leave them as fractions, but the more fractions we use, the more difficult it becomes to find a common denominator. And we know we cannot add fractions if they don't have a common denominator. So for this problem, that gives us the 1 over the equivalent resistance is equal to 0.454. The last time we worked with an equation that looked similar to this one, many of you tried to stop at this point. However, you're not done yet. We still have to get the equivalent resistance totally by itself. Right now it's in a fraction. Okay. So, if we rearrange this equation, we get 1 divided by 0.454 equals the equivalent resistance. When we divide this fraction, we get an answer of 2.2 ohms of resistance. The next part of our question asked us, what is the total current? We know from Ohm's law that voltage equals current times resistance. We can rearrange this equation to say that current equals voltage divided by resistance. We know from the diagram that the question provided us that we have a voltage of 8 volts. And we know from part A of the question that our resistance is 2.2 ohms. Current is our unknown, so we're going to write I equals a question mark. Now we can substitute our numbers into the equation. So we get I equals 8 divided by 2.2. And when we divide that fraction, we get a current of 3.64 amps. On to part C. Part C asks for the voltage across each resistor. Well, we know that we have a total voltage of 8 volts. We also know that for a parallel circuit, that the total voltage equals the voltage in resistor 1, which is equal to the voltage in resistor 2, which is equal to the voltage in resistor 3. So, each resistor must have a voltage of 8 volts. Again, because we started with a total of 8 volts and we're working with a parallel circuit where voltage total equals voltage 1, which equals voltage 2, and voltage 3, then each resistor must have a voltage of 8 volts. For the last part of our problem, part D, we're still working with a parallel circuit, but now it asks us to find the current drop across each resistor. It gives us a hint to apply Ohm's law to each resistor separately. Because it says to use Ohm's law, that must mean we need to start with the equation voltage equals current times resistance. Since it's asking us to find the current, we can rearrange this equation to say current equals voltage divided by resistance. We know that our voltage is always going to be 8 volts. But for the individual resistors, let's color code them. We'll do one in blue, the second in red, and the third in green. So for our blue resistor, we have a voltage of 8 volts and a resistance of 5 ohms. So our equation is going to say current equals 8 divided by 5, which equals 1.6 amps. Then for our red resistor, we have a voltage of 8 volts and a resistance of 7 ohms. So our current will be equal to 8 divided by 7, which equals 1.14 amps. Then for our green resistor, we have a voltage of 8 volts and a resistance of 9 ohms, which gives us 0.9 amps. If we take and add up all 3 of these currents, we get 3.64 amps. If we look back to the total current we calculated in part B of this sample problem, we also got 3.64 amps. That must mean that the individual current drops must add up to the total current. When we looked at series circuits yesterday, we found that that was true for the voltage in each resistor. So, as we compare the two types of circuits, voltage and current are opposite of each other when we go from series to parallel. And resistance is kind of opposite itself in that we use the reciprocal. The last slide you have in your notes is a summary of the equations we've talked about over the last 2 days. We have a list of things that apply for a series circuit. This includes how it looks in a schematic diagram, how we calculate the current, how we calculate the potential difference or the voltage, and how we calculate the equivalent resistance, which we know is also the total resistance. We include the same information for a parallel circuit. The key to being successful on these kinds of problems is going to be your ability to differentiate between series and parallel circuits.